Now we're ready to move on to looking at the concavity of the function and points of inflection. For that we will need the second derivative, and so we will use this form of the first derivative that we found in our previous work to help us continue our analysis. So our first derivative was e to the x times the quantity x squared plus 2x minus 4. So that leads us to the second derivative. Using the product rule, the derivative of the first factor is e to the x times the second factor, x squared plus 2x minus 4, plus the derivative of the second factor, that's 2x plus 2, times the first factor, which was e to the x. Now we have a common factor of e to the x, so we will go ahead and factor that out. And when I collect up like terms, I end up with x squared. Then I have a plus 2 to the x and another plus 2 to the x, so plus 2x and another plus 2x. That gives us a plus 4x. And then I have a minus 4 and a plus 2, so that makes this a minus 2. So our second derivative is e to the x times the quantity x squared plus 4x minus 2. Now we investigate the presence of critical points. So the first location or source of critical points is where our second derivative is equal to 0. That means e to the x times the quantity x squared plus 4x minus 2 equals 0. Note that e to the x is never 0. So the only way this equation can be solved, or the only source of solutions for this equation, is when we have x squared plus 4x minus 2 equal to 0. Now this equation cannot be factored, the quadratic cannot be factored, so we will use the quadratic formula. So x equals the opposite of b, which is 4, plus or minus the square root of b squared, or 4 squared, minus 4 times a, which is 1, and b, which is negative 2. This whole expression divided by 2a, and a is 1. This leaves us with x is equal to negative 4, plus or minus the square root of, now 4 squared is 16, and then we're going to add 8, so 16 plus 8 is 24, all over 2. Note that 24 is the product of 4 and 6, and 4 is a perfect square. So we will bring that outside the radical. So we have x equals negative 4 plus or minus the square root of 4, which is 2, times the square root of 6, all divided by 2. Now my numerator has a common factor of 2, so we'll factor that out. That leaves us with negative 2 plus or minus the square root of 6 divided by 2. The 2's simplify or divide out, leaving me with a 1. And so we see that our critical points are negative 2 plus square root of 6 and negative 2 minus square root of 6. So now these two critical points subdivide the real number line, or the x-axis, into 3 intervals on which we need to test the concavity of the function. So the first interval, going left to right, is negative infinity to negative 2 minus square root of 6. Then from negative 2 minus square root of 6 to negative 2 plus square root of 6. And then from negative 2 plus square root of 6 onward to infinity. And so we need to choose values in each of these intervals to test our second derivative. So in our first interval, from negative infinity to negative 2 minus square root of 6, we will check negative 10. So f double prime of negative 10 is equal to e to the negative 10 times negative 10 squared plus 4 times negative 10 minus 2. Remembering we're only interested in the sign of this value, e to the negative 10 is positive. Negative 10 squared minus 40 minus 2 will also be positive, and the product of two positive numbers is a positive number. So the second derivative is positive on that interval. Now we need to choose a value safely within the second interval, like something simple like 0. And we get e to the 0 is equal to 0 squared plus 4 times 0 minus 2. Now e to the 0 is positive, and 0 squared plus 4 times 0 minus 2 is negative, and the product of a positive and a negative number is negative. So our second derivative is negative on that interval. Choosing a value in our third interval, let's choose x equals 10. So then we can say that f double prime at 10 is e to the 10 times 10 squared plus 4 times 10 minus 2. And e to the 10 is positive, and 10 squared plus 4 times 10 minus 2 is also positive. The product of two positive numbers is positive. So our second derivative is positive on that third interval. So now we need to interpret what we've discovered. So when the second derivative is positive on an interval, the function itself is concave up on that interval. When the second derivative is negative on an interval, the function is concave down on that interval. And to our third interval, our second derivative is positive, so we know that the function is concave up on that interval. So we can declare that in terms of concavity, that our function is concave up on the intervals from negative infinity to negative 2 minus square root of 6, union negative 2 plus square root of 6 onward to infinity, and that it is concave down on the interval from negative 2 minus square root of 6 to negative 2 plus square root of 6. And now to consider points of inflection. Recall that we had 2 points, critical points, and both of these critical points are within the domain of the original function. Recall that our original function was f of x equals e to the x times x squared minus 4. With that in mind, then looking at critical point x equals negative 2 minus square root of 6, we can see that there is a change in concavity to the left of the critical point to the right, switching from concave up to concave down. And then for our critical point, x equals negative 2 plus square root of 6, we can see that there is a change in concavity from concave down to concave up at that critical point. So we do have, in fact, 2 points of inflection. So let's go ahead and find the y values that correspond to these points of inflection. So we have f of -2 minus square root of 6. That will be e to the -2 minus square root of 6 times -2 minus square root of 6 quantity squared minus 4, which is equal to e to the -2 minus square root of 6. Now if I square that perfect square, I will get 4 plus 4 square roots of 6 plus 6 minus 4. And the 4's will add to 0. And so we end up with e to the -2 minus square root of 6 times 4 square roots of 6 plus 6. So we have a point of inflection at our x value is -2 minus square root of 6, comma, and then our y value is e to the -2 minus square root of 6 times 4 square root of 6 plus 6. Now, checking or evaluating our second point of inflection, x coordinate, f at -2 plus square root of 6. We have e to the -2 plus square root of 6. Then we'll have -2 plus square root of 6, that quantity squared, minus 4, which gives us e to the -2 plus square root of 6 times, and now if I square this perfect square, I will get the -2 plus square root of 6 squared. I will get 4 minus 4 square roots of 6 plus 6 minus 4. And again, the 4 and the -4 will sum to 0. And I'm left with e to the -2 plus square root of 6 times the quantity -4 square root of 6 plus 6. So our second point of inflection is -2 plus the square root of 6 comma, e to the -2 plus square root of 6 times -4 square roots of 6 plus 6. There we have the concavity of the function along with the points of inflection. I hope you find this helpful.